Hello and welcome back. In this video, continuing our discussion of Chapter 13, we'll talk about thermal expansion and contraction. So I have three different dimensional objects up on the board here. I've got a linear object. You can think of this as a long, thin rod. I've got an object that is two-dimensional, like a thin sheet. And then I have a three-dimensional object, like a parallel pipage-shaped object. And when we heat or cool these different objects, we're going to see a change in the length for the linear object, the area for the two-dimensional object, and the volume for the three-dimensional object. And the formulas that govern the new length, the new area, and the new volume when we heat these different materials are listed just below the object. So let's go first of all to the linear object. L is the new length of the object. So the new length minus the old length is equal to alpha, which is the linear expansion coefficient. It's material specific. Different materials expand at different rates when you heat them. And so you would look this value up on a textbook. If this was a piece of brass, you would look up alpha for brass. If this was a piece of gold, you'd look up alpha for gold, etc. L naught is the length at temperature T naught, and then times the quantity T minus T naught. So if I take this equation and I solve for L, and knowing the new temperature that I heat the object to, the new temperature T, I can find the corresponding length L. Notice that if I heat the material, then the new temperature minus the old temperature is going to be a positive value. And so I will also have a positive value on this side, meaning the object will have increased in length. If instead I cool this object, then the new temperature is less than the old temperature, making this value in the parentheses negative. Therefore, this value on the left-hand side correspondingly will be negative, and the new length will be shorter than the old length. So when we heat a material, it expands, and when we cool a material, it contracts. Same type of formula governs the area expansion. So a new area A minus an old area A naught that is measured at some temperature T naught is going to be equal to 2 alpha, that's twice the linear expansion coefficient, times the old area A naught times the quantity T minus T naught, where 2 alpha, again, area expansion coefficient is twice the linear expansion coefficient for most materials. And then volume expansion. So if we have some volume and we heat it or cool it, the new volume minus the old volume is equal to the volume expansion coefficient, gets the symbol beta, times the old volume times the temperature T minus T naught. These temperatures, T and T naught, need to be in units of Celsius. And you'll see when you look up the values for alpha and beta on the table in your textbook or through a Google search that alpha and beta have units of inverse degrees Celsius. So you want to put your temperatures in degrees Celsius. So now let's just apply this thermal expansion concept to a real world issue, which is what's going to happen with global warming and the ocean rise. So estimate the increase in height for the Atlantic Ocean if the average temperature of the water increases by 2 degrees C. So what I've written down over here, and just through a little Google search, the area of the Atlantic Ocean, 76.76 times 10 to the 12 meters squared. That's the surface area of the Atlantic Ocean. And then the volume of the Atlantic Ocean is 3.10 times 10 to the 17th cubic meters. We're representing, oh, and lastly, I looked up the volume expansion coefficient for seawater. And it's important to note that the volume expansion coefficient varies as a function of temperature, and it also varies as a function of pressure. So as you move deeper into the Atlantic Ocean, the pressure increases, and as the pressure increases, the volume expansion coefficient also increases. However, as you move down in the Atlantic Ocean, the temperature decreases, and that makes the volume expansion coefficient decrease. So it gets quite complicated, but what we're going to do is just average the volume expansion coefficient for seawater as 100 times 10 to the minus 6 per degree C. So now we're going to estimate that the Atlantic Ocean is a parallelepiped. That's a three-dimensional rectangle. I have it drawn here, and it has some volume V naught at the current temperature T naught. And you see that if we estimate it as a parallelepiped, it has some height h and a surface area A. Now we heat up the Atlantic Ocean by 2 degrees C. And what happens is that we get an increase in height, but we're going to assume that the surface area does not change for this example. And so we still have a surface area A, but a new height h prime. And what we're tasked with to find is, what is this increase in height? What's the new height minus the old height equal to? So I've written the original volume here. I can take the surface area and multiply it by the height, and that gives me the original volume V naught. And now this new volume V, when we heat the material, is going to be equal to the surface area A times the new height h prime. So now we want to use the volume expansion formula that says V minus V naught is equal to beta V naught times T minus T naught. Now, we already know that T minus T naught is our 2 degrees C. That's the increase in the temperature. And we want to find what is the new height. So what I'm going to do is plug in values. I'm going to plug in the formula for V and also for V naught, and rewrite this formula in terms of areas and heights. So the volume V, the new volume, is going to be A times h prime minus the old volume, which is A times h. And that's going to be equal to beta times the old volume A times h times T minus T naught. And now you see here that the areas are all going to cancel. So all those areas cancel across the equation, and we need to solve for the original height h. Well, we can do that because we have the area and the volume. So let's go ahead and do that. So the height h can be written from this formula right here as V naught divided by the surface area. And so if we take V naught and divide it by the surface area, what do we get? So it's 3.10 to the 17th power. And we're going to divide that by 76.76 to the 12th power. And what we find is that the height is going to be 4.038 or 39 times 10 to the third units of meters, right? We're going to have meters cubed over meters squared. We'll have units of meters. So that's the original height. And you can see I already have h prime minus h on the left-hand side. So h prime minus h, which is what we're after, is going to be equal to beta. Beta is our 100 times 10 to the minus 6 per degrees C, times the original height, that's what we just calculated, 4.039 times 10 to the third meters, multiplied by our 2 degrees C. So you can see the degrees C is going to cancel. We're going to be left with units of meters. So if we multiply all of this together, we see we get and just one moment here. we get 0.81 meters. And of course, this is an approximation, but we see it's close to a meter. We have approximated the Atlantic Ocean as a parallelepiped, but we know that the Atlantic Ocean is actually more like a bowl. It is slanted on the side, so the surface area is actually a little bit larger than what we have calculated here. But this gives us a nice approximation for the effect of heating a very, very large body of water a very small amount. So what we did was take the Atlantic Ocean, approximate it as a parallelepiped with some original height and surface area, and saying that the surface area remains the same, heating it just increases then the height, and finding the new height then just involves finding the old, or finding the change in height is the old, the new height minus the old height. And using an approximation for the volume expansion coefficient allows us to approximate that as close to a meter, which is about a little shy of 3 feet. So it's quite a large increase in the level of the seawater, and the primary effect of the rise in the oceans is going to come from thermal expansion as we continue to heat our planet, burning these fossil fuels, putting more and more greenhouse gases up into the atmosphere, trapping more of the infrared radiation that's trying to radiate back out into space, re-reflecting it back onto the planet, adding energy, heating up the oceans. So gives you a real application using thermal expansion. So we will continue talking about Chapter 13 in the next video. We'll see you then.